Okay, and welcome to another video on this channel. So in this video, we're going to learn about recurrence and how do we represent recurrences in mathematical terms. As a little primer to the topic of recurrence, the topic is the pulse of computer science. Okay, let's proceed with one of the most celebrated examples in mathematics. This is the Fibonacci sequence, right? The gentleman that you can see on the screen is Fibonacci, and um, he is credited to have unveiled to us one of the best and most frequently seen sequences um, in nature and otherwise. Okay, so this sequence of numbers goes as follows, right? So there is a 1 in the beginning, and then the second element is also 1. Well, the third element is the sum of the first and the second element, right? So you see why the first and the second element is kept as same. One might also think a 0 to precede the first one, so that 0 plus 1 gives 1. But without loss of generality, we can assume that, okay, he started with two equal numbers. And then you see the same thing repeats, right? So 2 plus 3 gives us 5, and then 3 plus 5 gives us 8, and so on. So what happens here is that there are two consecutive numbers, let's say the third element and the fourth element, right? And then you add them up, 2 plus 3, you get 5. All right. Not only that, you look at, let's say, the seventh element and the eighth element. One is 13, another one is 21. Addition of them gives us 34. Correct. So there, it seems that there is an amazing pattern here which governs all the numbers in this sequence. Now, the question here is, as a mathematician and as a computer scientist, can we have a general formula, right? So, what do we mean by general formula? It means that let's say that we, give as input a particular number n into a magic box, right? And what comes out from here is the nth element of this recurrence relation, right? So can we get a general formula here, right? So an example of the general formula, you can see on the top right of the screen, I am writing a n as equal to n squared. So when n is equal to 1, right, 1 squared would be 1. When n is equal to 2, 2 squared will be 4, right? And when n is equal to 3, the square of 3 is 9, and so on. So you see the sequence 1, 4, 9, maybe 16, maybe 25, 36 is governed by the general formula an is equal to n square, right? So in recurrence relations, can we find out a general formula like this? That's the question, and we're going to find out whether we're going to find out the recurrence relation general formula in this video. Okay, let us look into a few more examples and try to discover what the general term is. You can see that there is a sequence 2n, right? And usually the values of n are taken greater than 0 strictly, or maybe non-negative integers. But there can be some recurrence relations where the value of n could be any integer that is conceivable. However, we would like to use the principle of well ordering in order to define a recurrence relation, saying that there will be a least number, and all of the other numbers will be increments of 1 or increments of 2. So basically, in our case, in our scenario over here, we will deal with a least number, let's say n naught, and all other natural numbers which are greater than and equal to n naught. All right. So let's say that let's choose the first sequence that is given here. A n is equal to twice of n. So the first considering n as equal to n not as equal to 0, the first number a0 is going to be 2 multiply 0, that is 0. The second one is 2 multiply 1, that is 2. The third one is 2 multiplied by 2, that is 4. The fourth one is 2 multiplied by 3, a3, right? So that is equal to 6, and so on. And similarly, we will have the last sequence as in that particular way. It is a little bit computationally heavier than the previous one, but you can take a pen and paper and try it out yourself. Also, as you can see, the other sequence, the general term of the second sequence is just 5. It means that this is the sequence of all the numbers, and all the numbers are equal to 5. So it is 5, 5, 5, 5, 5, and so on. It's an infinite sequence. But it has got a starting because the ordinals n are defined by the well ordering principle. All right, let's proceed to find out what is the recurrence relation. And as you can see on the bottom of the screen, a recurrence relation is written in such a way that the current general term is connected or dependent on its preceding term or one or more of the preceding terms. Right? Of course, there could be some examples in which the preceding terms are weighted by some constants, but nevertheless, the general term that you can see here is the general term, the recurrence relation for our Fibonacci sequence. Okay, now in our Fibonacci sequence, we have assumed that A1 is equal to 1 and A2 is equal to 1, right? So in these two cases, we will not consider an minus 2 and an minus 1, right? So these are the two things that we are not going to consider in this case. So an minus 2 will be basically equal to a of negative 1, and that cannot be defined by the well ordering principle in this case, but we will just assume that a1 is equal to 1 and a2 is equal to 1. And when n is equal to 3, so an will be equal to a3, right? So a3 will be a1 plus a2, and a1 is 1, a2 is 1, and the addition will give us 2. So this table is basically repetition of what we have seen a little while back. Okay, now how to solve this particular recurrence relation? So the method to solve this is basically to write everything on the left hand side, and just leave the zero on the right hand side. Correct? So basically we define something called the characteristic equation. And in the characteristic equation, we see which is the least term, right? The least term in terms of the subscripts that are written. So let's say we have got an, we have got an minus one, we have got an minus two. So an minus two is going to be the least term, and we assign one as the variable or maybe the parameter to map that. So 1 is basically k raised to the power 0, correct? And an minus 1 is the hierarchically a little higher than an minus 2. So we mention this as k raised to the power 1, right? And then we have got an, which is again hierarchically one more above an minus 1. So we mention that as k squared. So basically, the characteristic equation for the recurrence is given by Cn, which is the constant which was there previously. Cn minus 1 and Cn minus 2 are the constants. Instead of An, we write k squared. Instead of An minus 1, we write k. Instead of An minus 2, we write 1. And whatever we get from here is the characteristic equation. Okay, now the next step is to solve this characteristic equation. This characteristic equation, most cases it is a quadratic equation, but it might also be any other kind of an algebraic, higher order algebraic equation or a lower order algebraic equation as well. So we obtain the solutions of the quadratic equation. Let's say they are k1 and k2, right? So there are three cases which might happen. The first case is that the K1 is not equal to K2. And in that case, we write our general term as equal to A times K1 to the power n, B times K2 to the power n. Remember that this n are the variables for us, right? When we substitute the value of n as 1, we must get the original value of A1, right? Okay. Now this capital A and capital B are constants. And how do we extract the values of the constants? We substitute n as equal to 0 or 1 or 2. So these conditions are going to be given in our problem. Just to make things a little bit like clear, let's say that in our example of Fibonacci series, right? A1 is equal to 1 and A2 is equal to 1. So we substitute n is equal to 1 in the first and get one equation. We substitute n is equal to 2 and get another equation. And then finally we find out what are the values of A1, capital A and capital B, right? Okay. Now having said that, let's go to the next case in which the value of K1 is equal to K2. In that case, again, n is the variable, right? And n appears two times on the RHS, right? A and B are constants. A and B are constants. So again, what we do is that we substitute n is equal to 1 in this Fibonacci sequence, right? And n is equal to 2. And we write A1 as equal to 1 and A2 is equal to 2. We get two equations and we have got A and B are the variables, the unknown constants, right? We find out the values of them. And finally, there is another case where our um, our K1 and K2 are uh, are complex solutions, right? So K1 would be R cos theta plus I R sin theta, and K2 would be equal to R cos theta minus R I R sin theta. Okay, so if these are the solutions, of course, the solutions are going to be complex conjugate because our coefficients are all real coefficients. So in this case as well, we substitute n is equal to 1 or n is equal to 2, right? And we get a1 equal to 1 and a2 as equal to 1. In the Fibonacci example, the example might be different in your case, and then we find out the values of A and B. We substitute them here and we get the expression for AN. Right? So having said that, we have seen all the three cases in which we can substitute the values in the characteristic equation and back in our recurrence relations. Okay, thanks for watching. See you in the next one.